Good morning, guys. And in this today's session, we are going to see about the various categories of processor. And this is about the agenda about the development of electronics, how we started developing the electronics, and we are doing some processing using certain kind of processors and controllers. And this is about the today's agenda, and we are going to see about the different classification of processors, especially about the embedded system. First, we will see the first thing first. We will see in the development in electronics. For example, let us consider Intel 4004 is developed in 1971, and then in 2000 Intel Pentium 4 is being developed. So if you consider comparison, when compared with the Intel 4004 and the Intel Pentium 4, 2300 transistors are being involved in developing Intel 4004 board, while in Pentium 4 we are having 42 million transistors. See the difference. So there is a huge transition from 2300 transistor to 43,000, and also in terms of the processing speed from starting from the 108 kilohertz to 1.5 gigahertz. And in the present scenario, we have started developed INN and think about how the transition will be there. So in the initial transition, if the automobile speed has increased similarly as like this transition, we could reach now San Francisco to New York in about 13 seconds. So next we will see the basic processor. In any system, the processor is the heart of an embedded system. For an embedded system designers, knowledge of a processor and microcontroller is must. There are basic two units, functional two units are there for an effective operation of any processor. The first one is a control unit, that is we termed as a CU, and second one is execution unit. The control unit controls all the functional components in the processor. The execution unit deals with fetching the code and decoding it and then executing in the CPU of the processor. These operations are termed as fetch and execute. So this is the basic two operation of any processor. So various types of processor. There are three basic classification. The first one is a general purpose processor. The second one is an application specific processor, multi-processor system using general purpose processors. In the general purpose processor, again we are classified as microprocessor, microcontroller, embedded processor, and digital signal processor. First we'll see the microprocessor. So the microprocessor is a single chip semiconductor device also which is a computer on chip but not a complete computer. In CPU contains an arithmetic logical unit, a program counter, a stack pointer, some working register, a clock timing circuit, and an interrupt circuit on a single chip. To make a complete microcomputer, one must add memory, usually ROM, RAM, and memory decoder, an oscillator, and a number of serial and parallel ports to connect with the external world. So this is a microprocessor, and this diagram is a microprocessor, and termed as 8085, and which has to be placed over here. And in order to effectively operate and give the instruction, you need a keypad, and to see the what are actually happening, we need a display unit, and then some additional variables to connect with the external world. And also we have the oscillator and different dip switches are available in order to make the effective operation and also to deal with the functionalities of the processor. So the processor technology, the architecture of the computation engine used to implement the system desired functionality. The processor does not have to be a programmable, the processor not equal to general purpose processor. We are classifying the processor as a three major groups: the general purpose, application specific, and single purpose. We'll be seeing elaborately. So we will be seeing elaborately in the next presentation. The processor technology. The processor varies in customization for the problem at hand. So based upon the application requirement, we'll be using the different varieties of processor, starting on the general purpose and application specific and single purpose processor. While considering the general purpose processor, the programmable device used to be a variety of application, also known as microprocessor. The features it will have the program memory and general data path with a large register file and general ALU. And this is the data path. We'll be having the general ALU and also having the large value of the register file. The user benefits are low time to market and NRE cost. That is a non-recurrable engineering cost, and which is used for developing any kind of processor. Now, and a high flexibility, we can make it to do any kind of an application, and this is not a specific for a single bit of code. And you will be having the program memory as a open source, so that open source means you can program any, you can have any program inside this program memory. You can change it for any number of time, and you also use having the data memory and the control with the instruction register and the program counter. The Pentium, the most common, well known, but there are hundred of others. A single purpose processor. In a single purpose processor, the digital circuit doesn't execute exactly a single program. A single program is being executed in the single purpose processor. The features, it contains only one component needed to execute a single program, no program memory. There is a no program memory, so that you cannot feed any programs inside the system. There is a no program memory which is being available in the system, and you will be having the controller and data path and the data memory. The benefits are fast, low power, small size. In the application specific processor, programmable processor are optimized for the particular class of application, having the common characteristics and compromise between the general purpose and a single purpose processor. And there are certain program memory which has been optimized to do a single application. The features are program memory, optimized data path, and special functional units. So while comparing with a single purpose processor, it is having the program memory, sorry, and it is having the program memory, but it is being optimized to do a single application. The benefits are some flexibility, good performance, size, and power. Now, IC technology. The manner in which a digital implementation is mapped onto the IC. The integrated circuit, the IC technology differs in their customization. The ICs consist of numerous layers. There are varieties of micro level layers have been developed in the recent years, so that in order to reduce the size of any chip. The IC technology differs with respect to who builds each layer and when. The three IC technologies are fully custom VLSI, and semi-custom ASIC and PLD devices. The fully custom VLSIs are very large-scale integrated circuit, and semi-custom ASIC which has a gate array and standard cell, so that we can customize this ASIC design to any kind of an application. The PLD is a programmable logic devices, which also used for any implementing any complex functionalities, which can be reconfigured with any number of time, not as like your application specific processor. The fully custom VLSI. So all layers are optimized for embedded system, particularly a digital implementation, such as placing transistor, sizing transistor, and routing wires. The benefits are excellent performance, small size, and low power. The drawbacks are high NRE cost, long time to market. In order to produce a single assay, we need to wait for a so long time for the development, and also its development cost is very much huge when compared with the other kind of processors. The semi-customs, the lower layers are fully or partially built. The designers are left with routing of wires and maybe placing some blocks. Benefits are good performance, good size, less NRE cost than the fully custom implementation. The drawback still requires a few weeks to months to develop. The next one is your PLD devices. So all layers are already exist. The designers can purchase an IC. The connections on the ICs are either created or destroyed to implement a desired functionality. Such as the example is the FPGA devices, that is a field programmable gate array, are very much popular in the market. The benefits are low NRE cost, almost instant IC availability. The drawbacks are bigger, expensive, and power hungry and slower devices. The next one is another part of a microprocessor. And the next one is we're going to see is a microcontroller. The microcontroller is a functional computer system on chip. It contains the processor, memories, and the programmable input and output variables. The microcontroller includes an integrated CPU, memory. The memory has a small amount of RAM, program memory, and both, and the peripherals are capable of input and output. The various microcontrollers made by different manufacturers are Intel, PIC, and Motorola, and there are several in the series. So these are the very different series of Intel processor, Intel controllers 8031, 3251, 8052, 87, 51, 8752. In the PIC family, you will be having the 8-bit, 16-bit, and 32-bit, and also now 64 bits are being evolved. The PIC 16 and PIC 18 are famous for doing the small scale projects. The Motorola MC68 and HC11. And this is the varieties of the microcontroller, and there are several on the series. The basic classification between the microprocessor and microcontrollers are the functional blocks are ALU registers, timing, and control units. The microcontroller it controls the functional block of microprocessor, and in addition, it has a timer, parallel IO, RAM, EPROM, ADC, and DAC. The in microprocessor, bit handling instruction is less, one or two type only. Many type of bit handling instructions are available. You can monitor any of the bits in the microcontroller, but that is not possible in the microprocessor. The rapid movement of code and the data between external memory and the microprocessor. So you can transfer the bulk data between the microprocessor and the external memory. The rapid movement of the code and data is within microcontroller. We cannot easily transfer to the external world. We have to use any of the serial communication. You cannot transfer by connecting to the USB or some other devices. It is used for designing the general purpose digital computer system, and they are used for designing the application specific dedicated systems. Now this is the basic classification, and there are still more differences are available when comparing with the microprocessor and microcontroller. Next one is embedded processor. The special microprocessor and microcontroller are often called as embedded processors. A embedded processor is used when the fast and context switching and automatic ALU operations are needed. Examples are ARM7, Intel i960, AMD 29050. The digital signal processor. Digital signal processor are generally called as general purpose processor and is a single chip VLSI unit. It includes the computational capability of a microprocessor and multiply and accumulate units, so-called MAC units. The DSP has a large number of applications such as image processing, audio, video, and telecommunication processing system. It is used when the signal processing functions are to be processed fast. Examples are TMS 320 series, Shark, Motorola 5600 series. So this is for used for implementing any of the signal processing. For example, we can go for the image processing unit which is available in a digital camera, and also the signal processing unit which is used in audio Yamaha boards, Yamaha piano boards, digital boards. Next one is application specific system processors. The application specific system processor, the ASSP, is dedicated to specific tasks and provides faster solutions. The application specific system processor is used as an additional processing unit and for running the application in place of using the embedded software. The examples are IIM 7100, W31100A. So multi-processor system using GPP. So nowadays the people are using the mobile phones. It's having the dual core, quad core, and octa core functionalities. Basically the core technologies are that both all the cores may be a single homogeneous processor or it may be a heterogeneous processor. The single core can be used for the general purpose, and a single core is used for the graphics functionality, and a single core is used for the animations functionality, and a single core is used for the camera functionality. It may be classified. So similarly, the multiple processors are used when the single processor does not meet the needs of the different task. The operation of all the processors are synchronized to obtain the optimum performance. So, at the last, we are going to see about the Moore's law. The Moore's law describes a long-term trend in the history of computing hardware. Since the invention of integrated circuit in 1958, The number of transistors that can be placed inexpensively on an integrated circuit has increased exponentially and doubling approximately every 2 years. The trend was first discovered by Intel co-founder Gordon E. Murray in 1965. Almost every measure of the capability of digital electronics devices is linked to Murray's law: processing speed, memory capacity, and etc. So this is a pictorial representation from the year 1960 to 2010. So, and this is there were transistors per die we can able to accommodate. So starting from the same 1000, we are having the 4 giga transistor, giga units of transistor we can able to accommodate in a single processor. And this is how the Murray's law has changed the development of system on chip from the yesterday's world to today's world. So we can have the n number of RTL functionality inside the today's SOC environment. In the olden days, we are having the processor, memory, and the one or two RTL functionality and general purpose IO. And today's we are having the control processor and then memory unit, and also we are able to accommodate a digital signal processor unit and memory unit and n number of real functionality units such as RTL and real-time I/O. The growing number of transistors on an SoC drives the trend towards more RTL blocks on the chips. The other hardwares which can be included in the embedded systems are power source, clock oscillator, real-time clock, reset, and power-up reset, and watchdog timer reset, the memory, I/O ports, and I/O buses, interrupt handler, DAC, that is a digital to analog system, and a ADC, analog to digital conversion, LCD and LED displays. And the software part, we can able to develop the any kind of embedded software by using the C programming, C++, .NET, and this is for the PIC microcontroller, MASM, and RIDE. And these are the compilers we are used for developing a embedded software. That is a RIDE, Kale, and a microchip. There are many more in the line. The application for embedded systems, which can be used for household appliances, audio players, integrated systems in aircraft and missile, cellular telephones, electric and electronics motor controller, engine controllers in automobiles, calculators, medical equipments, video games, and digital musical instruments. And thank you. And before closing up, we'll be seeing on a case study and how what are the different embedded systems that have been used by BMW 850i brake and stability control system. So in anti-lock braking system, pumps the brakes to reduce the skidding. So automatic stability control system, that is the AAC plus T, controls the engine to improve the stability. The ABS and the AAC plus T communicate. The ABS was first needed to interface with the existing ABS module. And this is how the sensors for the each wheels are being connected. This is the front wheel and this is the back two wheels, the sensors and the brake, and along with that the ABS center, which everything is being controlled by the central ABS control unit, which has a hydraulic pump to control all the brakes to avoid skidding when there is a sudden emergency rises. This is the example of an automatic application. Today, the high-end automobile have the 100 microprocessors. The 4-bit microcontroller checks seat belt, and microcontroller runs the dashboard services, and 32-bit microprocessor control the engines. So these are the variety of microprocessors are being involved, which varies from 4-bit to 16-bit and 32 bits for controlling each and every parameters. The alternate means longer design time but allows a higher performance. The microprocessor, programmable logic, gate array, standard cell, and fully custom. The last three is ASIC based, and the next one, the programmable logic, is a CPLD and FPGA devices, and microprocessor is a microprocessor and DSP based. So when there is a change in the transition in each and every unit, there is an increase in performance. And also the fully custom, to develop the fully custom ASIC, we need a higher time, design time. For developing the microprocessor based system, we need a less amount of time, and also the performance very much less when compared to the fully custom ASIC. So thus, the microprocessor are used as a key component in the embedded system design, and the programmable logic and ASIC are used for a critical part in the design. An objective for an embedded system designer is to find the cheapest solution that meets the requirement. Do not use a Pentium when you only want to control the freezer. So So thank you for the session. End of the session. We come to the end of the session 2, and we will be seeing the next session in another day. Thank you.